So in practice, the computations, I think, will work. But conceptually, it should be, instead of a 2x2 matrix, a 4-element column vector.
Exactly. Let's say the final result will be okay. What Jayang Lee is doing is going to be okay, the final result. But the process that you are using, as Pau is saying, you are lucky that you get the good result. But the process, if we want to do it in another exercise, we need to understand the general process, right? So Pau was, I mean, I don't know who, Pau, was it you who had this solution ready? Or it was Joaquim? Okay, so maybe we should leave Joaquim. Okay, let's do something, Zhang. Why don't you finish your computation, okay? And then Joaquim will show us that it's the same outcome, but that the matrix needs to be 4 times 4. I think it's going to be more efficient.
Yes.
Okay.
Yes.
Go on. Yeah.
Okay.
Thank you.
Nothing.
So Jayang, you can go on. It's fine. No. Jayang, it's okay. Go on. Make your correction.
Okay.
Make the exercise as you wanted to do it. So Pau is saying, okay, let's say sometimes you get so the result is going to be correct, but the process, Joaquim will explain it later. But I think it's good that since you are here, that you explain us what you did. I think this is good because as Pau is saying, you get the same result, but it's good to understand why we get the same result. So I think it's good even that the final result is going to be correct. So it's good that you show us your method, okay? And then Joaquim will do the method. So go on, Jayang, you're welcome.
Yes, which is equal to 0, 1 minus 1, 0 times minus y2 minus y1 minus x2 x1 is equal to minus x2 x1 minus y2 y1. So we write it xl is equal to minus x minus x2 x1 minus y2 y1. So we can get a Poisson bracket HL is equal to DH acting on XL is equal to X1. DH is equal to the X1, X2, Y1, Y2. XL is equal to this minus X2, X1 minus Y2, Y1. So we can get this is equal to X1 minus X1, X2 plus X1, X2 minus Y1, Y2 plus Y1, Y2. So we can get it is equal to 0. That's all.
Yeah, that's.
This is my solution.
Yeah, thank you very much. That was indeed very good idea that you go on the Blackboard, because, well, the solution is correct. I mean, your let's say your use of the bracket, exactly the last computation it's perfect, and indeed what we learned from your resolution is that, okay, this is a notational, this is a way that you have to compute this, notationally,
Yeah.
yeah. But let's say it's a free resolution, okay? Because if we
Yes.
apply the definitions that we gave in class, then let's say the result is going to be the same. Let's say, but the intermediate process is going to be the resolution a little bit different, okay? But the final
Okay.
result is correct. Because indeed what happens is that observe, and that's very interesting that we have here in the last line, that indeed the thing you had to do is to check that the different, that x1, what you wrote exactly cancels out differential of h. And you were able to interpret this 4x4 matrix as this line matrix. Okay, but now
Yes.
Joaquin
Okay.
is going to go on and do a computation in such a way you also get this one column matrix, but let's say in a more canonical way, okay, or let's say official way, following more or less the definition. So I thank you very much for your participation. This was very good, Janja. And yeah, thanks for this. I'll leave the word to Joaquin.
Thank you. So I stop it.
Okay. Yeah, thank you for your participation. Let's see if this is working. Okay. Wait a second because I'm recording as well. So this can be seen. Well, okay. Yeah, actually there are.
They are
there
recording it, Joaquin. It happened
Oh yeah,
that
I can stop my.
Yeah, but
Well,
we need,
I will keep the whole recording as well.
yeah, this is what I was going to say. I'll put the more complete one. Well, I mean, okay, good.
Okay.
Sorry.
So there are two ways in which we can think of this exercise in this case. So the first one is as Zheyang Li did. So we can think of the theoretical definition of the Poisson bracket, which in this case. Second, my pen needs to wake up again. So the first one is thinking of the definition of the Poisson bracket in the context of a symplectic manifold. So, all right, as you did. I don't know why is this not painting right now. Okay, sorry, I will just do a new note. All right. So the Poisson bracket of two functions is indeed the contraction by the symplectic structure of the differentials, which is precisely the same as applying, for instance, the differential of G to the symplectic vector field, the Hamiltonian vector field corresponding to F. In this case, F and G are, of course, the energy and the angular momentum for our function. And indeed, our whole debate was about the right notation to use for this Hamiltonian vector field. The main issue was basically that the inconsistency, because first the differential was a row vector and then it was a square matrix, but the process was all right and the result was, of course, all right. And if you want to do this in general, you can think that XF, if you want to think on coordinates, right? This is the matrix. Let me think, how would you do it? I think you would pair, yeah, okay, you will pair this way. So you will have this matrix, and here you will have the the column vector in this case of the partial derivative. So partial of f with respect to x1, so on and so forth until partial of f with respect to y2. Right. So this is mainly the idea that you are pairing the x coordinate with the y coordinate and the corresponding index. So everything here is just one way to look at this. Another way is looking at the specific structure that we have in this case. In this case, we have the basic structure. We have the standard symplectic structure, if you will, in Darboux coordinates. So in this case, you can just use the standard formula for the Poisson bracket. So you have here the sum for I from 1 to n, where n is 1/2 of the total dimension. So the dimension of the base manifold, if you are thinking of the cotangent bundle, and you just need to pair the derivatives. So xi here partial of y minus partial h with respect to yi and partial of l with respect to xi. And here, I don't know, but yeah, I can close this. So if you apply this formula, you can, here n is equal to 2. So you basically have the same factors that you computed. So basically the result of the computation is exactly the same in this case. So I don't know if it's worth to write it out, as you prefer. Eva, what do you think? You want the whole computation? You're muted, sorry.
Well, I think that it's very good that today Zhang Li went on the blackboard. I'm sorry, Zhang Li, I'm not pronouncing your name correctly. I apologize. How do we pronounce your name? The previous student. Can you pronounce your name? Yeah. Zhang Li? How do we pronounce it? I mean, is it correct?
Oh, Li Jiayang.
Jiayang. Okay.
Yes.
Jiayang. Yeah, I think that today that the fact that Jiayang went to the blackboard was very good, because I think we understood that maybe, Joachim, it's good to pursue this computation. So Joachim is asking me, should I go on with this computation? I think it's a good idea, because then we will see how the computation that Joachim is doing fits the same computation that Zhang Li did. Okay, so I think Joachim, go on and do the whole computation. I think it's good. Let's be very basic today.
Yes.
No problem.
Okay, thank you.
Okay, so let's expand this. So this is partial of h with respect to x1 times partial of l with respect to y1 minus partial h with respect to y1 times partial of l with respect to x1, and the same for the index 2. So here we will just need to replace this for the correct partial derivatives. 1 second, so that I can write everything out. Here, partial of h with respect to y2 and partial of the momentum with respect to x2. All right, so one by one, partial of h with respect to x1. Here I don't have the, for some reason I cannot bring this to the other node, but let's take a look here. The partial differentials of h with respect to each coordinate are basically the same coordinates, right? So partial of h with respect to x1 is x1, partial of h with respect to x2 is x2, partial of h with respect to y1 is y1, and partial of h with respect to y2 is y2. So this won't be a problem. And for the momentum, maybe we can come back from time to time. But basically, we are pairing the coordinate with the different coordinate with the different index. So if we come back here, what we have here is, all right, for the partial of h with respect to x1. Well, as we said, this is x1. Partial of L with respect to y1. We can go back here, blah, blah. Okay, this is minus x2. And I won't do this much more often because this takes much time. So this is minus x2. Okay. Now we have minus sign. We have the partial of h with respect to y1. This is y1 again. Partial of L with respect to x1. We can check back, but this is basically y2. The partial of h with respect to x2. We have it. The partial of L with respect to y2. This is the positive component. It's the other one. So this is x1. Finally, minus the partial of h with respect to y2. This is y2. And the partial of L with respect to x2. This is minus y1. Hopefully, everything is all right. And here we can see that, okay, this minus and this minus at the end cancel out. So this is positive in the end. And we don't have any other minus canceling. We have the first component is negative, of course. So now we can start just crossing out what's repeated. The first component is minus x1 times x2. It's the same as the third component. So it cancels out. Minus y1, y2, it cancels out. This is with the fourth one. So this is 0.
Okay, observe that if you write, for instance, this computation that you did before, the matrix, this is what I was referring to compare to what Zhang Yaling, I'm not good. Jiayang, to what she did, observe that indeed, if you take this, go a little bit lower, Joaquim, show me the line. Yeah, exactly, this line. Well, this line a little bit lower, just a little bit. Okay. Yeah, now observe that this product that we have here of the partial derivatives of h is what we can write like she did on the language of the matrix. We can write this as the product of this 2 times 2 matrix. So yes, it's a matter of notation. Okay, this is what I was writing in the chat. It's not that it was wrong, it's a notational thing. But the thing that what she did works well with the standard symplectic form. But what happens if we don't have the standard symplectic form? Then we need to use the method that Joaquim is explaining. Okay. Yes. And that's why I think it was very good. Thank you very much for your participation, because we could see you didn't make an error. This is what I was trying to write in Chinese, of course, using Google Translator, that you don't have to worry. I mean, it was good that you explain us this argument, and it's good to compare it to the general argument, because it also gives you a hint how to do these computations with matrices. And if for you it's better to compute in the other way, as we understand that it's a notational matter, it's okay. Okay, so thank you very much. I think. Thank you very much.
Thank you.
So it's good. I mean, thank you very much. I mean, it's a pity that we don't have a third problem session, because I'm enjoying a lot people going on the Blackboard and people trying. I mean, and it's very good. If you don't try, you don't get it. So that's perfect. I'm not going to interrupt Joaquin. Go on. This was very good.
That's great. Just to add on top of what you said, that's absolutely true. To unify the two approaches, generally, if you have a local expression of your symplectic form, you have the matrix. What you can write in this case is here the partial derivatives of H. So you have the column, the row vector in this case. Here you have your matrix. So we call it J, which in the standard case is the one we wrote before. This one, the zeros and identity and minus identity. And
Yes.
here you just add a column vector. So this is how you can generalize this for any, indeed, any symplectic structure in this case. Okay. Let's see if there are more questions.
Perfect. That was a good point.
All right.
Okay. And in the case, yeah. So thanks a lot.
Yeah, thank you very much.
Very good. I think it was convenient that she went on the whiteboard because we all understood something new. Okay, that indeed in the four-dimensional case, then you have the magic that you can even write it as in this 2 times 2 way. So it's a good notation. But if we do it in general, it's good to use what Joaquin is explaining. Okay.
Mm-hmm.
Thanks a lot. So let's go on, Joaquin. I let you. I'm going to shut up. I'm sorry.
Don't worry. All right. So our original plan was to start with the modular vector field exercise. I will do it fully, and then I will leave it to Pau to work on the exercises on moment maps and so on. But maybe, Pau, what do you think? Maybe you should take it from here, and if we have more time in the end, I can talk about modular vector fields if people are interested. What do you think?
I think maybe it's a good idea. I mean, I was planning to do exercises 3, 4, 5, and 6, but maybe we can do 3 and 4, because I think we have Pablo who will do the number 4, and then after 3 and 4, we can switch to number 1, and then 5 and 6 if we have time. I don't know if we will be able to do everything, but if you agree, we can do now 3 and 4. What do you think?
Yeah.
Yeah.
I mean, exercise 6 is very interesting, huh? So it would be good. Yeah, I think it's a good plan. Yeah. I think what Pau proposed makes a lot of sense.
Yeah, if anyone has any other requests, just feel free to put it on chat, and we can adapt. Yeah. Okay.
Put
so
it
I
on
will start
chat to speak up. Yeah.
Yeah, or speak up indeed.
Yes. You can interrupt at any point, and we love your participation. So I will share my screen, and I will do number 3, and then I will invite Pablo to do number 4, which are kind of similar, but number 4 is even more, well, we will see that it's even more interesting, because with the moment map, with the image of the moment map, we have to do some special things that we don't do in the symplectic case, but we can do in the bisymplectic case. In fact, we need to do it in order to have a smooth moment map, smooth image in the moment map. So I will start sharing my screen. It's my second screen. I think you can see it now with the first slide. And let's try to do number 1.3, in which we ask that in the B-sphere, in the bisymplectic manifold, which is a B-sphere with the singular submanifold as the equator, with this bisymplectic form here, we ask to consider the S1 action of rotations around the z-axis, the vertical axis, to consider the vector field coming from this rotation, and to draw, to compute the moment map, and to draw the image of this B moment map. So the moment map, we have to say first that we will be able to compute the moment map at every point except on the singular hypersurface, because there it's not defined. We will not be able to compute since the coordinate explodes in some sense. But in the bisymplectic case, you know that we take this exploding coordinate and we deal it as if it was smooth. This is our trick here. But to start, let's see how do we compute in general a moment map in coordinates in these bisymplectic coordinates. So we have this the flow. We will be considering the S1 action, which gives a flow, gives a vector field that we will call X, which in this case, well, this sign depends only on the direction of rotation, but it wouldn't mind if we did not take the sign. And then we want to see what happens with this flow. This flow is in fact, is a diffeomorphism of the sphere on itself, and we are looking for a moment map of this action which is a Hamiltonian action. So we are looking for a moment map, for the moment map mu, we'll call it mu, which satisfies the following condition, which satisfies, in this case, which has to satisfy that the differential of this mu will be, in this case, this X, this vector field, this Hamiltonian vector field, we want it to be minus the vector field in the theta direction with omega. And at this point, I will say that there's a matter of sign here. Some authors put a sign here in the moment of definition here. Some authors don't put it. It doesn't matter. In fact, it's only a change of if you're working in one dimension, it's only a change of sign of the image of the moment map. If you are working in 2 dimensions, maybe the image that you would have on the first quadrant, you have it on the 3rd quadrant. So it's, for instance, I think I will do it in this case without the sign, but if you do it with the sign, you obtain basically the same, structurally the same moment map. Eva is putting his head here because the sign is an important thing, but let's see.
Well, but you can spin in the other direction. I prefer that you say you can spin the other direction. If you spin in the other direction, it's like changing the sign. Then I don't feel
yes. I mean,
it's like I'm
in
like,
fact,
well, you know, well, people don't know this, but there was even a war along the, let's say, in the States. People who were in Berkeley were putting a plus, people in MIT were putting a minus. I am a collaborator of Victor Guillemin, and I feel like I am putting, if I don't put a minus, I am just going to the Berkeley group. So
so we can put a minus here. We could erase the minus in the vector field and it would be essentially the same action. So
yes,
this minus at the end.
we could also, exactly. We just, but it's not so bad. You can also, you can also spin in the other direction and then you get a minus.
Yeah, so let's see if,
and I feel like I am not stabbing my collaborator at MIT. Okay, well, that's cool.
So what happens here? We know we want a mu which satisfies this equality, and in fact this equality is basically what we get, knowing that this omega that we have here is 1 over h dh wedge d theta. In this case, since there's a change of sign because d theta is the second element in the wedge product, we obtain now it's a plus because it cancels with this minus here. So we obtain a plus 1 over h dh. And we need a mu which satisfies this equality here. So we want that the right hand of the equation has the form, has the aspect, the shape of the differential of a function, and we know that we can achieve it thanks to the logarithm function. So this is equivalent, and at this point we can equal these two, the left side part of the equation and the right hand side of the equation, to obtain that mu could be any at first could be any function of this form, logarithm of absolute value of h plus a constant, but we take this constant to be 0 in order that it works. And essentially we conclude that the moment map of this action, this B symplectic, this B action in which we consider a B symplectic manifold, sorry, a Lie group acting on a B symplectic manifold, has this following action, which is not smooth at 0, but if we consider it in all the manifold except for the singular surface, so in M minus Z, we have a proper moment map here. But let's see which is the, sorry, I think I missed this sign precisely here, no? Now, if I take this this convention,
yes,
it appears a sign here. So what we have here now, the second part of the exercise, and maybe the most interesting part, the new thing, because we know how to compute moment maps in symplectic geometry, but what happens in B-symplectic geometry when we want to draw this moment map, which is the aspect of this moment map. And Pablo will do the same in the next exercise, and the idea will be the same. So we have this moment map. Sorry, I will.
This is the next exercise. Okay.
We have to draw this moment map. So I will draw first the manifold. What we have here is the sphere. We took the common coordinates for the sphere, kind of cylindrical coordinates for the sphere, in which we took h. The singular hypersurface was this one. This was z. And we considered the S1 action of rotations in theta. This gave us these rotations. The moment map has the following aspect. If we want to draw, the moment map, let's consider the image of mu, and let's see what happens with the points in the B-symplectic sphere. For every circle in the I will draw it in another color. For every circle in the sphere, the image of the moment map is a value that goes, in this case, to the positive part of the real numbers of the line in the right. But this happens also, I mean, both circles in the northern hemisphere and in the southern hemisphere, due to the absolute value, go to the upper part of the real line. So the image, well, let's start with the easiest point, the image of the North Pole. Since the North Pole has coordinate h equal to 1, goes to the 0. So logarithm of 1 is 0. So the image of the northern pole goes to 0. So 0 is in the image of the moment map, of this moment map. But the same happens with the southern pole. So the southern pole goes to 0 too. If we take the other circles, we see that for each circle, all the points in the circle go to a certain value, which is positive here, because they have coordinate h between 0 and 1 in absolute value. The logarithm of a point of a value between 0 and is negative, but since we have a minus sign, it is positive. So there's circles in the northern hemisphere and the southern hemisphere that all of them go to the positive part of the image of the real line. So, and what happens now when we approach the singular hypersurface, when we approach the equator, when we take a circle which is really close to the equator, we obtain a really big value of the moment map. So when we tend to the equator, we cover all the positive part of the moment map. So the image of the moment map, in this case, if we want to know which is the image of the moment map, it will be basically all the positive the positive numbers. But we want it in some sense to be a polytope, no, a convex polytope in the sense of del Zan, and thanks to the theorem of Attila, Guillemin, and Stemmer, we know that for a symplectic manifold, this moment map would have a convex image, and we want in some sense that it happens the same, that it has a convex image here. But what's happening here is that there's kind of two copies of R plus here. So the entire northern hemisphere is mapped to R plus. So the image of mu restricted to, let's say, the northern hemisphere is a copy of R plus, and the image of mu restricted to, let's say, the southern hemisphere is also R plus. So we have two copies of R plus here. I mean, every point in the image has two circles, which are its pre-images. So what we construct now is a point which is at infinity, and we associate the image of the moment map of the equator of the singular manifold, which you could think that it's not defined. We associate to it the infinite point. So we say that the image of the equator via the moment map would be the infinite here. In this way, we can glue the two copies of R plus we have. So we have that, I will take another color. We have that all these circles in the southern hemisphere are mapped to R plus, and all the circles in the northern hemisphere are mapped to another copy of R plus. What we do is to add an extra point here, which is infinity, and which is the image. For us, it is the image of the singular hypersurface, and we say that it's placed at infinity, and we can glue this. We can make it continuous. If we think it of a zigzag pattern, no, we could translate it to, well, I will like zoom in this image. What we do is to consider that the moment map, the image of the moment map is kind of this pattern. No? We have for each circle, for each circle in the southern hemisphere, we have a point in R plus. When we arrive at the equator, we have the point at infinity. And when we cross the equator and arrive to the circles in the northern hemisphere, we have for each circle a point also in R plus. So in fact, this is continuous. I mean, there's a family of circles, a continuous family of circles in the northern hemisphere and in the southern hemisphere. So the idea of the moment map of an action on a bisymplectic manifold is that we will have these infinite points, but if we take a number of copies that then in number 6 I will talk about how you can already see, no? But how many copies of R or of a half line or a half plane do we need to construct this image of the map? So as many copies as the connected components of M minus Z, exactly. So this is more or less what we asked. In fact, we didn't ask you that you construct this zigzag pattern, no, but you can think of it as an extra from Eva class, in which she already introduced the big toric manifolds. And in number 4, we will see that we can do the same in the case of the torus, but we will need to add 2 points at infinity, since we have since Z has 2 connected components, and for each one of them we will need to add a point at infinity. So I will not spoil anything more about number 4 because I leave it to Pablo. I don't know if Pablo was planning to do this construction at the end. I mean, Pablo, now you can do what you were planning to do. I mean, what we asked in the resolution of number 4. And if you took this idea of adding this point at infinity, you can add it to your resolution at the end and see what happens, which is the shape, which is the form of the moment map when we add this point.
I didn't do it, but I have followed, and I think I will explain what happens in the toric case.
I think you can. It's a little different in this case because you take the image is all R, not R plus, but I think you can improvise it now.
I will improvise it.
So I will stop sharing my screen.
Yes. Okay, so I will share screen, Zoom, start transmission. Okay, yes, I am sharing now. And well, wait. Okay, now. So I thought I would start a new node because now that we are sort of doing all the computations, I mean, when I write problems, I sort of do sketchy computations and then guess the result. But if we are to solve the problem, okay, I will do the computations as they should be made, and then I will jump to the other node to show the actual p c infinity function. So just I wanted to say a few things. First, my handwriting is very poor, very poor. So just stop me if you need to.
No
second,
problem,
to the group.
I do not want to be that guy, but I think because I come from Xavi Gracia, which Eva knows, and Xavi Gracia is very picky with things, so I have that tradition too. I think this should be open. I think, but whatever.
It's related to what Pau is saying.
Yes, I know, but if we are to compute coordinates in a chart, because I think
well, yeah,
these are coordinates in a chart, you can extend them later, but
yeah. The thing is that when you extend them, man, yeah, you are right.
Okay.
Correct.
And I wanted to say a thing which is not quite related to the problem, but I wanted to say how I understand the moment map and why for me it has to carry a minus sign. Because
okay, good. Fantastic, Pablo, you are in the good team.
I know, even though I am
you are collaborating with people in Berkeley.
With I don't know if Kolya would agree with me.
No, Kolya is not from the group of Alan Weissman.
Okay. So for me, how do I understand the moment map? For me, when we arrive to Hamiltonian group actions, you take a group action, mu, which comes from a Lie group G onto the group of symplectomorphisms of a manifold, and you sort of, as Eva explained, you ask the action to act infinitesimally through Hamiltonian vector fields, but not just through Hamiltonian vector fields, but in a controlled way. And she said that this controlled way is the moment map. I like to understand this picture through the comoment map, and I will try to explain what this is. Because when you have
Pablo, thanks for this. I think this is a good compliment to the class. Thank you.
Because to say that a Lie group action acts infinitesimally means to consider its infinitesimal action. And to act through Hamiltonian vector fields just means to say, well, I have I just consider another object, which is the, I like to have, well, I have a differential geometry notation, which does not quite agree with symplectic geometers, but I say that this action is mu hat. Hat is for the infinitesimal version. So I transform this in the category of Lie algebras. We have this, and we ask that this acts on the set of Hamiltonian vector fields. And because of a theorem by Lie, this has to be an anti-homomorphism, because we are saying that this is a group action. So this has to be an anti-homomorphism. And in fact, the conditions on a moment map, the linearity, sort of, you could say, and the equivariance follow from requiring the moment map not to act directly on Hamiltonian vector fields, but rather on Hamiltonians themselves. So you could say that a moment map, if this is the assignation of a Hamiltonian vector field, you would require, and this is the dual notion, which is a moment map, you would ask an arrow to be lifted to the Hamiltonians, and this would be, this is a bad notation, poor notation because I am saying this is a group action, and moment map will be mu as well. So I will say this is M, this is M hat, and this is M hat. And you are requiring a comoment map. I don't know how to, maybe with a star, I don't know. So this is a comoment map. You are, for an action to be Hamiltonian, you are not just requiring that it acts on Hamiltonian vector fields, but rather on Hamiltonians themselves, and that the fundamental vector fields are the symplectic gradient of this action on Hamiltonians. And if you require this action or this moment map to be a Lie morphism or anti-homomorphism, you recover equivariance. This has to be checked. But why do I put a minus sign? Because if we said that Hamiltonian vector fields are homomorphisms, and I have an anti-homomorphism here, this has to be an anti-homomorphism. So it has to carry a minus. Sorry. And that's why I think that it should carry a minus. And I hope to have clarified a bit my understanding of the moment map. I mean, it was hard for me to understand the moment map, and this is the picture that I took. So with this said, with this said, we can start the exercise, and the exercise is actually just a straightforward computation. Just compute the.
One question: can you relate this? And I mean, just to put this a little bit in context with an assignment that we had. We had an assignment in the list that if you do the bracket of two functions, you get the Poisson bracket of the two functions. You did the Lie bracket goes to the Poisson bracket.
Yes, this is a Lie algebra morphism, and in the fact that this is a homomorphism comes from the minus, and that is something I wanted to say in other problem which I didn't get to do the last class, but Eva told, well, I will put this minus here in the proof of Moses' theorem or Darboux theorem through Moses' trick, and she said, I need this minus for some term to cancel out.
Yeah,
that is true. And in fact, if you want to see that the Hamiltonian vector field or Hamiltonian designation, when you define the canonical Poisson bracket through the symplectic form, is a homomorphism of Lie algebras, you have to put the minus. If you don't put the minus, you will have an anti-homomorphism.
Exactly.
And in fact, if you don't put a minus there, then you don't put a minus in the moment map. And you should have, this would be an anti-homomorphism, and this would be a homomorphism, and everything would be okay. But if you put a minus in the definition.
So the question is, what do you want? What do you prefer? Would you prefer to be an anti-homomorphism or? That's your question. So I think you clarified. Exactly. So the assignment. So what Pablo is doing in a very categorical way, because he didn't say it when he introduced himself, but he's a categorical guy. This is good to be surrounded by people who like categories, people who prefer to do things in coordinates, is that the arrow that we have up there, the arrow that he's putting up there is exactly this assignment, that the bracket of the Poisson bracket goes of functions goes to the bracket of Hamiltonian vector fields.
Yes.
And that's a very good way to put it. I like it, Pablo.
Thank you.
That's
how I understood it.
That's good.
Okay, so now
today, we are full of surprises here. We are learning plenty of things. This is very interesting. Okay.
Now I have to get my hands dirty and throw out some computations, because life sometimes requires you to compute things. And we will, to compute the Hamiltonian vector field, this is the way I compute it. I think it surely must not be the best way to do it, but it's my way. I just contract. I just see how it acts on forms or on vector fields, and just from there I continue. So to see what we were asked to check the Hamiltonian of the rotation on the θ2 coordinates. So I have to contract this with θ2 omega. We are asked to see what is this. And what I do is just contract this with a vector field x in coordinates. This is omega partial theta 2 x, which is this is d theta 1 sine theta 1 wedge d theta 2 partial theta 2 x. And when we compute this, this will be d theta 1 acting on the partial of theta 2, which is 0. So this is 0 sine theta 1 times x theta 2 minus, and now d theta 1 acts on x. So this would be x theta 1 divided by the sine of theta 1 times, and now d theta 2 acts on the partial of theta 2. So this is 1. So this is minus x theta 1 sine theta 1, and this is the contraction of minus d theta 1 divided sine theta 1 with the vector field x. This is how I write contractions, because I told you my notation comes from differential geometry. But so we get that the contraction is actually minus d theta 1 divided by the sine of theta 1. And this, if you take the smooth part where everything is well defined, which was what we were commenting earlier, if I am not mistaken, which I could be, this is minus the differential of the logarithm, I think that you write log, of the tangent of theta 1 halves. This should be the what we get. And now I didn't do this when I solved the problem, because as I told you, I am lazy. That's maybe why I like categories. But this, you could wonder, is this smooth? Well, no, it is not. This fails to be smooth in the set Z, which is the disjoint union of phi 1 equals 0 union theta, not phi. Phi 1 equals pi. And this is the 0 set. But is this smooth in the context of B-symplectic geometry? Well, it is, because we were saying that the set of B C infinity functions on a manifold is a constant times the logarithm in absolute value of a function f plus g, where C is a constant and f and g are C infinity smooth functions. So I think this is clearly a B C infinity symplectic function, because we are taking f to be tangent of theta 1 halves in the non-zero set, whatever, and g to be 0. So this is okay. And now if we want to draw this function, well, I can draw some quick sketches, and I can draw here r. So this is r, this is pi, let's say this is 2 pi. So if I draw the absolute value of the tangent of theta 1 halves, oops. At 0, this is 0. And we've got here, well, at 2 pi, this is 0. And the tangent explodes at, well, the tangent itself explodes at pi halves. But as we have a 2 dividing here, this explodes at pi. So let me just say this is the point where everything explodes. And now we can draw the tangent. I am very bad at drawing. This is sort of the shape it has. And if we apply a logarithm, but this is not pencil. If we apply a logarithm, then I know the 0 goes to minus infinity, and that's basically it. This would be pi. Well, this would be 2 pi. We'd have this here, and this would go to minus infinity. I don't know quite the shape. Something like this, maybe. And at 2 pi, this would also explode because at 2 pi we had that the function was 0. This is basically the shape it has as a dependence on θ1. So now this is constant on θ2 coordinates, and we can sort of try to guess what it looks like. These are some other problems. It looks something like this. So we have θ1, I will try to draw here, and maybe I can erase it later. But we have θ1 here. This is the 0 z. And as we said, this function is constant on θ2. So that's why we have dependence. This is the rotation on θ2. So the function is the same on rotations by θ2. And θ1 goes in this way. And that is why we have here the picture of R. But I know I'm just limited by human capabilities and time and laziness. So I have not been able to draw smoother, but red means going to infinity, blue-ish means going to minus infinity, and you can sort of think how it explodes. And to finish this idea, I will try to express what Pau said in terms of this moment map, which I didn't do here. I can try to. And taking inspiration from Pau, let me see here. I can draw R in a similar way, which I have done here. And let's look at this picture here. So we have, following the scheme that Pau said, we have two components. We have here this component and here this component, which correspond to the connected components of the manifold minus the 0 set. So if we take these two components, and well, this is not what I wanted to do, and we come here, these components would be, let's say I take two different colors, which I don't know, this purple over here, for instance. I say this is one connected component, and its image is all R, because we see that at θ1 it explodes to minus infinity, and at pi it explodes to plus infinity. And we can do the same for the other component, another color that is well distinguished. Let's say this. We have this connected component, whose image is all R as well, because at θ1 equals pi it explodes, and at 0 it explodes to minus infinity. So if we take the process that Pau said, which is to glue pieces at the critical set, we have to take a point here that glues both images, and a point here which glues both images, here and here and here and here. And if we join everything, this would be essentially the same as a circle, which is not a circle. I don't know what this is, but should be close to a circle. So this, as Eva told once, this is what is known as a circular valued moment map. And I cannot further explain, or I cannot explain something which Anastasia could not explain better than me. So I guess this is my solution. I don't know if there is something wrong, something which you want to add, any of you?
Well, this is very nice, Paulo. So first of all, thank you. And your picture is so nice. And the solution was
I think
was
your
super.
picture should be now the new icon for the web page. I think I will put this picture in the web page of the course. Let's vote. What do you prefer? I think this handmade picture is adorable. If you can send me a screenshot, I will put it there. It's very nice.
I would have to make it a bit better, because this is, I mean, it took some time, but this is obviously not as good as it should be or could be or whatever.
But it looks very natural, you know.
Yeah,
like
it looks very
the
clear.
process of solving a problem.
Yeah.
Thank you very much.
Now we'll
Really
take
nice.
this approach. And Chung is connected. Good morning, Chung.
Yeah, sorry, I was like 15 minutes late this morning.
You missed a lot of fun.
Yeah, I mean, I really like this. I really like this. And actually, I have a small question regarding to the very nice remark given by Pablo just now regarding to the untyped morphism and morphism.
Mhm.
So I might be wrong. I just want to say that since in general, I think this kind of diagram can be given by considering the exponential map and the joint action when you consider the infinitesimal generator, and it is at that moment that you have taken a differentiation. So can I say whether the minus sign comes out or not actually depends on if you consider your group action as right action or left action.
A good point.
Yes, I think it
because if you consider the right action, then normally when you consider the Poisson brackets, there will be a minus sign coming out, right? So I was wondering if that is the reason why we got.
That's a very deep reason. That's a good point. I mean, who uses transformations on the right? You'll be surprised how many people do this. I mean, we tend to use the left transformations, but this is a good point. I mean, indeed, yeah, I like both explanations, the one by Pablo and this thing, because what Chung is putting on the table is that behind all the moment map structure, we are also taking into account the group and how the group acts on the manifold. And we could make it out on the left or on the right. That's true, indeed. When you do things on the right, so said in other words, if I had talked about transformations on the right, then I had to be very careful about that the fact that if you do a right transformation, right, then you need to change a sign. Precisely, this is what we do, for instance, in the coadjoint orbit application. And we do this because multiplying on the right, it doesn't match the sign. It will be good. That's a good point. We could leave it as an exercise. What happens with this if you take the that's a good point. If you take the transformations on the right. I mean, I thought everyone was taking transformations on the left until, well, I mean, I realized many people are working on the right, on transformations on the right for some reason. Sometimes because you take a reduction and then it makes sense to act naturally still on the right. So that makes a lot of sense. That's a good point, Chung. Thank you.
Okay, thank you.
Well,
I don't know if Pablo wants to add something. I just jumped on it.
No, I think that's all I wanted to say, and that's even more that I wanted to say. But Pau gave me a good basis to speak about moment maps and how I see moment maps. So I just wanted to take the chance.
Yeah, I think that's a very good thing, Pablo. This is very well explained. I'm enjoying a lot the class. I guess I think I enjoy more the class when I'm not doing it, like when I'm just in the audience, like my friends. My friends are still, by the way, the guys who are watching these classes still don't have names. Remember that you can choose a name for these guys, the popcorn guys. Still don't have a name here. With my duck. This is another story. This is for the general talk. Okay, let's go back in business. Okay. I'm sorry, we have 6 minutes, which will be 12 so maybe.
I will stop sharing now. Okay, that should be.
Thank you.
Thank you very much.
So we have 6 minutes left. What do you think we can do, Joaquin? Because we could continue with problem 5 or 6, or we could do some small part of number 1. I don't know, Eva. What do you think?
If
we are with maps, the most natural thing would be to do the next exercise in the list. And then what I think is that the modular computation is important, because I got questions from people in the audience about this computation. Okay,
yeah,
so what I'm going to, I propose the following, that Pau does the problem as he can on this construction of examples of toric manifolds. And then maybe, Joachim, I can leave you 10 minutes of my next class to do this modular, 15 minutes. Well, I don't know if you're available on Thursday. We can take a quarter of an hour of the next class. I think it doesn't harm if to do this computation of modular weight and the obstruction theory, because this fits very well into when I talk about big contact, the obstruction theory part. It's related to a very recent theorem about non-obstructions in the contact case. So I would like to have this exercise maybe solved. Do you think you can take it? You can take 20 minutes of the class, Joachim, and do this next Thursday.
Thing is, what I wanted to say is that doing the computations well will take much more time, because it's doing the local coordinates computations and also the obstruction theory, for which we need to explain well what the Poisson cohomology is. Maybe we can do it. What I want to propose
without
is
the Poisson cohomology. No, the exercise of Cavalcanti, for instance. We don't need the Poisson.
Okay, you mean that one. Yeah. What I wanted to propose is, instead of that, if you can do your exercise, Pau. Otherwise, I could do a schema of how the modular vector field matches inside of the B symplectic case. What's the fact that it's transverse to the symplectic leaves and so on and so forth.
Yeah,
but I can do that drawing at the beginning of next class, maybe, or during.
Let's see what people prefer. Let's vote. Who wants toric manifolds now, and who wants modular vector fields? I don't know. I think it's more natural to do an exercise in toric manifolds now. And then Joachim, I am the host now, by the way. And then Joachim, I have the power. I am the host, it says. Joachim, then at the beginning of next class, we will discuss, we will give priority to two on the problem on the list, because I think it's good to do first the computation of, I think what you are saying, it's good. We can reserve, I can give you
in any case, the computations are done in detail in the solutions, which will be posted. So that can always be found.
Yeah. So let's do, Pau, go on and do next exercise.
Okay, let's try to do.
We have voted, we have counted the votes, and you win.
So we will take a few more minutes, because we will not be able to finish in 2 minutes, but let's try. Let's try to do it completely. So exercise 5, in fact, I will share screen and I say that exercise 5 and exercise 6 are really connected, because in number 5, which is this one that you can see in the screen, we ask for the description of the external polytope of a B-symplectic toric manifold for the lowest dimension cases. Since we know about the Delsan polytope theory, we know, and the statement says that the external polytope is a Delsan polytope. We could describe this external polytope, and we could, in some sense, deduce which is the B polytope of the manifold in these two cases, in case of n equal to 1 and case n equal to 2. But I will go directly to exercise 6, and then maybe some things that I comment while I'm doing number 6 will be useful for number 5. But essentially what we ask in number 5 is essentially theory about Delsan polytope, since in dimension n equal to 1, the Delsan polytope is a point, and in dimension n equal to 2, the Delsan polytope is a segment. So there's no mystery about the external polytope, but the interesting point of number 5 was to think, okay, which is the B Delsan polytope, not the external polytope, which is a restriction of the B Delsan polytope, but the complete B Delsan. But let's go to number 6, in which we ask to compute the moment map of the toric action of the two-dimensional torus on the complex plane, the complex projective plane, given by this action of rotations. No? Then we construct a bitoric manifold applying symplectic blowups and the gomp sum, this symplectic sum, this connected sum on the manifold that we have after the symplectic blowups, starting from CP2. I will do it kind of first. I will do the computations of the moment map, but then I will do this blow up pictorially. So Eva didn't explain the blow up technically. I will not do it neither, but I will send you a good reference from Vial Carson, in which she focuses on the blow up and specifically on examples of blow up of CP2. So I will. To start, let's compute the moment map of the historic action on CP2 given by this rotation on the second and third coordinates, homogeneous coordinates of CP2. So on Z1 and Z2. So to start, let's consider an easy case of rotation. Let's see which is the moment map of the most basic case. No, before starting to compute directly the rotation, let's get the intuition about which will be the moment map of a rotation in the complex plane, not the complex projective plane, but only the complex plane. So let's consider this rotation. Sorry, I don't want to write in red, but consider this action. No? Consider this action from S1 on the complex plane given by the rotation. No? Let's take an element of S1, an element of the complex plane, and map it to a rotation of angle G. The moment map of this, to compute the moment map of this action, we could use a complex coordinate, but it's easier in this case to pass to real coordinates, since we know which is the vector field. We know by her which is the vector field corresponding to a rotation around the origin. No, we know that this induce. Let's say that we are considering this action M, and M induces vector field, a vector field on C, or we can think that it induces vector field on R2, which is the following one. Is the vector field that corresponds to rotations. We know it by heart, as I said. No, if you have done a basic course on dynamical systems or on differential equations, you know that this gives rotations. This gives rotations around the axis.
I mean, if people want to do computation, it's just compute the derivative of respect to t with this product that you have done with z, x, y, and evaluate at t equal to 0. Okay, this is. I think this can be a good exercise. Not bad that people.
Yes. So what there says is another way to compute it directly, but anyways, compute it as you want. That what you get is the equation for the moment map that you get here is this one. You construct this vector field with the symplectic form. Let's put a minus here, and we find the following condition. We have that minus x dx minus y dy has to be minus this differential, and so the conclusion is that mu has to be the differential. Sorry, the differential of mu is the differential of x squared divided by 2 plus y squared divided by 2. This is in real coordinates. So in complex coordinates, we will have that the moment map is the square of z divided by 2. So this is to get the intuition about what happens, which is the moment map of rotations. Basically, the moment of rotations is this square of the components. This is quite natural because we know that rotations preserve circles. So the moment map, the conserved quantity, is is the radius of the circle. So we could say that we already knew it by heart too. And let's see now what happens in the case of two rotations acting on two coordinates of the complex positive space in homogeneous coordinates. That is what we are looking for. But first, let's do the same, but now with two torus acting on. Let's see what happens in. Let's do it in C3, not the complex projective plane, sorry, but C3, in order to see that it happens the same. So if we take two elements of, an element of C3, which I call Z0, Z1, Z2, and I apply a rotation only on the second and the third components, let's do it in the same way with the exponential of I theta 1 Z1 and exponential of I theta 2 Z2. With the same procedure, we would arrive to a moment map which is really, really similar. A moment map which would have now an image not in R but in R2. It has two components: the image of the moment map and the moment map of Z0, Z1, and Z2 would be basically the same in two components: Z1 squared divided by 2 and Z2 squared divided by 2. What happens if we work on the complex projective plane and if we do it in complex coordinates? What we have is quite similar than to what we have here, but now we don't work with the coordinates of C3, but the coordinates of CP2. Sorry, this is a P, so CP2, and this rotation on the homogeneous coordinates on CP2, that you can think, well, what's CP2? It's difficult to have an image of CP2. It's a four-dimensional manifold. If you think of the real projective plane, then you can think that it's the same, but in every point is a complex point. And the real projective plane, you can think of it as an Euclidean plane with the points at infinity also considered as points. So you add in the infinite lines as a boundary. Well, not as a boundary, but you also consider infinite lines. This is for the real projective plane, and then you think that you have the that you take homogeneous coordinates. I will give a brief explanation that what are homogeneous coordinates. I don't know if everyone here is familiar. It's a thing that you see in the lectures a few times, but then you forget it. It happened to me also. And what we have here is essentially the same. You have a rotation in the second and third coordinates, but since they are written in homogeneous coordinates, you can kind of normalize. You can I call it normalize because it's like putting a limit, putting the infinite at 1. So we will divide it by the modulus of this sphere, of this complex sphere, this homogeneous sphere we have here. But essentially what we do is to normalize the moment map that we have for the complex for C3 to the complex projective plane. And as I said, I will not enter into details, but what you can think of it, since we call that CP3 is essentially C3 minus the 0 quotiented by C minus the 0. You can think that you can think on the Hopf vibration, and the Hopf vibration, I don't know neither if you are familiar with the Hopf vibration, but the Hopf vibration, the complex Hopf vibration in this case, sends the sphere S5 to CP2, and you can also think of an embedding of the complex, the three-dimensional, the sphere, the S5 sphere on C3, which is a 6-dimensional manifold. So this, you can embed this here, and there's a Hopf vibration that takes also S5 to CP2. Via these these two connections, you can think that you take the moment map we had here. I will circle in blue, and somewhat normalize it to obtain the following moment map for the case of CP2 in homogeneous coordinates. What you obtain here for the moment map is essentially the same, but normalized by this factor, which would be like this constant sphere here in S5, or if you can think of it embedded in C3. So it's the same moment map, but divided by the module of Z0 plus Z1 squared plus Z2 squared. So it's kind of a normalization, as I said. So we would have this moment map for this action on Z2 on CP2. So this moment map. Now let's take a look at this moment map. Let's go. Let's find the fixed points of this moment map. We know about convexity theorem of Atiyah, Guillem, and Sternberg. We know about Derzan theorem, and we know that the fixed points of this moment map. So sorry, the fixed points of this action will be the vertices of the convex polytope corresponding to this moment map, which at this point is a toric moment map. It's symplectic. It's not bisymplectic. It's symplectic, and let's draw it. We know that there are three vertices in this moment map. We know this will be a triangle then, and we can see that the fixed points are the following ones. The fixed points of this action. Of this action, which I would call M, are, of course, the 1, 0, 0 in homogeneous coordinates, the 0, 1, 0, and the 0, 0, 1. These are fixed points of this action, and their images are. Let's compute it. If we compute their images, they. Let me do it in a new slide. The images of these 3 points. Let's see if it works. What I'm doing now here. Okay, it seems to work. Where are they mapped via the moment map? No, these 3 points go to 0. 1/2, 0, and if I'm correct, they go to these 3 points. So now we can draw, since we know that these will be the vertices of the Derzan polytope, we can draw the moment map of this action, and we know that this triangle is the image of the moment map. It's a convex polytope in dimension 2 in R2, and is the image of this action on CP2. This is the Derzan polytope corresponding to this action. Now let's try to attack the question we were asking for. Now we were asked to construct now a big toric manifold applying symplectic blow up and the Gauss sum, the symplectic sum on this polytope. So I didn't know. In fact, I'm seeing now I have the statement, and we apply the symplectic blow up, but we have to do it thinking on the polytope better than thinking on the manifold. So symplectic blow ups are done, and now this is the point where I will send in the chat the reference of the article of Yal Carson, which is a really good reference for. I will send directly the archive link, since it's what I have it. Easy to see where's the chat here. Now I don't find the chat. I don't know if, okay, the chat is here. Since I'm sharing a screen. Okay, the chat
Yeah,
is here.
sometimes you can move, well, yeah. Can you find it? If you
Yes.
move the, okay.
Yes. So this is an article of Jan Carson and Leah Kessler, in which they precisely consider circle and torus actions and symplectic blow-ups on CP2. In there, they also reference other authors, which also contribute to them. In fact, Guillermin and Stenberg, they also have papers dealing with this question. And the idea that Eva also introduced on the theory session is that via symplectic cut we can cut and then glue the manifold in order to have a new manifold. But at this point, since we don't have a bisymplectic manifold, we have to say that to construct a B-symplectic manifold after blowups, we should start with a manifold which is already bisymplectic. So by symplectic cuts, we don't achieve a bisymplectic manifold by only doing symplectic cuts. But if we start with a bisymplectic manifold, we can obtain new bisymplectic manifolds via symplectic cuts, a more complex manifold. So a really easy example I can put of a bisymplectic manifold which has a moment map that you know is this actually is this manifold. No? If we consider the product of a B sphere times a symplectic normal sphere, as I mentioned too, we know that this moment map is a square that that goes from -1 to 1 in both directions, but that has a singular segment here, which is the equator of this sphere. So the moment map would have
one interruption I want to do. So in this picture, this means that this would be like my red points, no? That
yes,
something is at infinity here.
Exactly. So yes, in fact, yes, you say points. Okay, it's true. This line of points which are infinity. And what we are going to do with the delta and polytope corresponding to a triangle is basically the same, but you have to imagine that there's a line of points here, which would be points at infinity, that we will not cut. We will do symplectic cutting, but we will be careful in order not to cut this line of points here, which correspond to the singular surface, but to cut on one space or on the other space. If we had more connected components of Z, we could have more lines here. So we could have more lines in the polytope, but let's do an example in which we have only one connected component of Z. What we can do now is to do these symplectic cuts here on the CP3, and let's observe that what we have now is an example which has only 3 fixed points, which are these ones. What happens if we apply symplectic cut on not on a vertex, but near a vertex of this construction? So if we apply a symplectic cut here, what we have is that we obtain a new. Sorry, I will do it in a way that we can see the evolution of the moment map, the image of the moment map. So I'm going to cut here, sorry, here, also here, and also here. I'm going to apply 3 symplectic cuttings, and then if I apply these cuttings, what we obtain is a new polytope, which by the design corresponds to a module symplectic morphism, corresponds to a unique manifold, a unique B-toric manifold. But how many fixed points do we have here? Since we know that fixed points correspond to vertices, we have 6 fixed points here due to these 3 symplectic blowups. There have appeared 3 more vertices, 3 more fixed points of this action. Let me draw the axis again.
So you could go on and on and doing more cuts and cuts.
I could go on and on doing more cuts and cuts, but let's say something about which is this manifold that we have here. We have to take into account the orientation that we have at each of the two sides of the moment map that it's divided by a line. So there's as Joachim explained the other day, you take orientations and this is the reason that you cannot have an odd number of connected components of Z in a torus, for instance. And for instance, if this is the plus orientation in your bisymplectic manifold and this is the minus orientation, what you would obtain here is a combination of CP2, or sorry, not CR2, but CP2 oriented in a positive way with the sum of CP2 oriented in a negative way. It depends on which side are you doing the cuts. In this case, if I did not have a symplectic manifold and I took all the a bisymplectic manifold and I took all the, I mean, if it was not the red line here, what I would obtain would be this manifold. I could take the negative orientation for the 3 cuts I have done here. These 3 would correspond to the 3 cuts I have done, and they would have the same orientation. Since in this case, I have done 1 cut in 1/2 of the line and 2 cuts on the other half of the line, this would not be a 3, but we would have a 2 here and a 2 here. So one CP2 is the one that we have at the beginning. Another CP2 with the same positive orientations, we have obtained it from this cut here, and the 2 copies of CP2 obtained but with negative orientations are obtained from these 2 cuts we have applied on the other side of the singular hypersurface on the bisymplectic manifold. So we could go on if now we cut this polytope at 3 other points, we could obtain a manifold which has even 12 fixed points. I don't know if I will be able to expand this, but it's my objective to make it bigger. But I don't know if I can make an image bigger with I don't think I can make it bigger, but let's imagine I cut it again at the 6 vertices, near the 6 vertices we have here. What we would obtain is a new polytope, which has 12 fixed points, and which would be, for instance, as a copy of 10 CPs, some of them with an orientation, a positive orientation, and another of them with negative orientations. In fact, if it was not a bisymplectic manifold, but only a symplectic manifold, it would be, we can describe it, and it would be CP plus 9 CP2 with a negative orientations. If we applied this,
so if we didn't have the red, if we didn't have this red line, if we didn't have this
exactly, if we didn't have the red line, everything would be oriented the same way. But if we have singular lines here corresponding to the singular hypersurfaces, we have to take care in which way they are oriented. In which side they are of the red line. So in which way they are oriented. So maybe they could add up on this side or on this side. So they well, depends on your manifold. So this is this has been, well, not that quick. I wanted it to be quick. I have taken more time.
No, but this is very good because this is not in our paper. In our paper, we do a hand waving thing, and this is very concrete. This is an actual construction. So we would have here, like, indeed, this is a good way to realize manifolds as bisymplectic, bitoric symplectic, which cannot be toric symplectic. Okay. So yes. If you look at the literature, well, if you look at this, at the slides in which I projected examples that cannot be symplectic, but they can be symplectic. And on the top of that, we have proof more. We can see that they can be toric bisymplectic, or bitoric symplectic, bitoric
Yes,
bisymplectic.
exactly. Since there is a polytope that we can construct, we know that the manifold does exist. So we can work with the polytopes to create this new
This is very good. So this is a whole theory, and the truth is that, well, the complete reduction theory for bisymplectic manifolds is something that Anastasia is doing in her thesis. This is something that still is not on the archive, but should be in the archive soonish. And then we give also as soon as possible. We will give the reduction for groups that are not necessarily toric. And what is very interesting is that this connects to very classical examples. But okay, people want to go to sleep or to eat, depending on where they are, or to have breakfast if they are in Toronto. And so maybe we should stop here, but this is a very good point to stop, because in the next class, so remember that I changed a little bit the order, and indeed the order I think it's better, because now the next class is about big contact structures, and again we will reconnect with the examples in celestial mechanics, and I will prove the existence of a new family of periodic orbits. But I will also tell you something about the obstruction theory there. Let's say if I give you a manifold, is there a topological reason why this manifold cannot admit such or such a structure? And this class of today connects very well, because we saw this last example about also manifolds that can admit not only a bisymplectic structure, but also a toric action, okay, bitoric action, that cannot admit a symplectic structure. So indeed, this whole theory is not very well understood. And that's why I was inviting Joaquim to talk about the obstruction theorem, where it's true that the problems are solved in the list. But maybe I will discuss this with Joaquim as you wish. You think
we can talk about the solution next session.
Yeah, we can talk about the solution. Maybe you can just show the solution that are already solved and comment it a little bit, because this will be a good introduction. Like now I take a form that is not, will be not symplectic. It's going to be contact. And then, do we have some constraints? That will be the one of the questions that we will answer on Thursday. So on Thursday, we will consider obstruction theory for contact. We will see that it's much more easy in the contact case than in the symplectic case, thanks to the work of Eliasberg, of course. And then we will go back to this motivation of celestial mechanics, the restricted three-body problem. Okay, I'll take the computation that we didn't do, because we did a computation of the restricted three-body problem, but it was symplectic. Now what I will do is to see what is the contact structure induced, and then we will discover, and this will be the end of the class, that there exists a family of infinite periodic orbits that it's new. This was not understood before. And this will be fantastic, because we couldn't do this without the power of bisymplectic geometry. And then, well, the last session will be about the Weinstein conjecture and so on. That it's something that I will start describing maybe on Thursday, but I will attack it in a more serious way. And the connection of a problem in celestial mechanics to the resolution of Karen Uhlenbeck, a resolution of Karen Uhlenbeck of problems in analysis. And this is, we will use one of the theorems that gave Karen Uhlenbeck the Abel Prize. And this will be a very good end of the course, okay? And then, of course, we will have left a lot of things in the pipeline, because I would have enjoyed to have another problem session like the one of today. I have really enjoyed it a lot. But, well, I mean, sometimes it's good to leave, you know, as we say in Spanish, dejamos con el caramelo en la boca. We live with this idea that, oh, we could do another session. Okay, maybe we can discuss if we do another problem session, but I don't know. I am very happy with the session of today. I have enjoyed it a lot. And myself, I have learned a lot of new things. Like, I liked a lot the approach that we got today of Zhang Ya Li,
家阳, Li Jiayang.
Jiayang. Okay, thank you. And I have
Excuse
enjoyed a
me.
lot the. Thank you very much.
I also want to ask some questions about this exercise.
Of Pau.
Number 6. Yes.
Okay, go ahead.
When we consider when you compute the moment map in this exercise, how you get the vector field?
How you get the vector fields?
How do you get the rotation?
This is the computation that I was sketchy.
Yes. We consider CP2 is even equivalent to C3 minus orange.
So
right.
you are asking for the vector field in the case of CP2 directly.
Yeah. So I think she's asking how you compute the fundamental vector fields.
Yes, how you get the vector field.
So when you have this action, which is the exponential, well, this computation that I said, you do it like this. Maybe it's good that you do. Can you share the screen and do an actual computation now, like of the action, of the initial action, that you have an exponential and you are multiplying by z, and this is x1, x2. So how do you get the rotations vector field? I think that this is what you're asking, right?
Yes. And I don't understand how you consider the alignment coordinates in this exercise.
Okay. So let's start. Maybe. Well, Pau, go on.
Well, no. I
thank you.
I don't know if I have understood correctly what you mean. I mean, you want to compute the exponential. Sorry, this derivation with respect to t.
Yes, I don't know how you get this vector field.
Sorry, do you want to know how do I get this vector field?
Oh, yes.
Okay.
From the action.
Well, you can think of it in a lot of ways, which is I always think of it from dynamical systems, because but you can think of it as if you have.
So if you take the exponential, Pau, and you do the derivative with respect to t, and you put z instead of z x, y, then when you evaluate at t equal to 0, you are going to get the actual coefficients. Because.
Let's see. So let's see. You mean that you take.
Exactly.
As if you were going to compute the infinitesimal generator, what you obtain here is exactly, okay, that's, now if you think, well, if you think, what do you obtain here at t equal to 0 is exactly z. So if you have a dynamical systems in which z dot is iz, what's happening here is a rotation of 90 degrees. So if you now take real coordinates, so if you take real coordinates, you know that.
You plug z x plus I y, maybe it's the quickest thing to identify. So if you plug again, if you write.
Yes, that's true. Yes, I will do it in this way. Okay.
I mean, what you are saying is correct. It's totally correct. I mean, from this expression, you know that it's a rotation. But now let's assume that we don't know.
Yes.
This.
No. Okay. That's right. Let's do it.
Now you need to show me how you do the cut and paste. I'm very impressed. I need to take classes from Pau.
So what we do have here, if we apply here directly complex coordinates, so real this z in the form x plus iy, what we have is ix minus y. And we want this to be the derivative, so the differential with respect to time of z dot, but z dot is basically x dot plus I y dot. So what we have here is x dot equals the real part is this one, and the complex part gives us this equation. So basically, well, I'm using a notation of dynamical systems, but basically what we have is that this is this vector field. So this is this vector field. If you write it in a more differential geometry way, this is this vector field. This is minus y in the x direction plus x in the y direction. Sorry, because I'm really used to dynamical systems notation, but
no, this is very good.
Don't worry
got
about
it. I mean, observe what I was saying is that the vector field that you have up there in complex, it's already this vector field. But well, you have identified the differential equation too, which is great. I think this is very good. Wow.
Yes.
You agree? Okay.
I have another question. I don't understand how you consider the element coordinates in this exercise. In this exercise, we use the element coordinates.
We use the yes. There's the homogeneous coordinates, which are this one.
Yes.
You're asking more or less how do they work?
How you consider it? I don't understand.
Okay, what are these coordinates? Basically, well, I could put an example. The most easy example is the real projective line, in which we can also take homogeneous coordinates. If we take RP1, which is the most basic example in which we can use homogeneous coordinates. If we consider RP1, which is the most basic example of a projective space, a real projective space, there you use these coordinates. You use these coordinates. You can think of x and y, or of x0 and x1. And how do they work? So you use these coordinates, but you are not free. I mean, you identify with x and y any coordinate which has both of them, which are multiples of x and y. So there's an equivalence relation in which you identify this as the same element in RP1. So for you, for instance, the element 1, 2 is the same element as the element, for instance, 3, 6. This is the same element. So the idea is to extend this, well, and I have to say another thing. You are considering all the points, all the combinations of x and y, except the 0, 0. So x and y cannot be 0 at the same time. So this is an element which is not in RP1. So 0, 0 does not have any sense in the projective space. So 0, 0 does not exist here. It doesn't have any sense. X and y cannot be 0 at the same time. And a convention that it's commonly used is to consider only this set of coordinates. You consider the points of the form, for instance, x1 for any x in the reals, union this single point, the point 1, 0. This is the complete real projective line. So here you can see that it's a one-dimensional space. It's not a two-dimensional space. That you could think that it's a two-dimensional space since you see two coordinates, but it's a space of one dimension, of one dimension, since you only have here an infinite one-dimensional set, and here a single element. You can think of it I think that a good way to think of it is as a direction. So you can think of it as a vector. So you know that a vector which is multiple of a vector is more or less, it's essentially the same direction, which is this equivalency idea. But if you consider vectors in which you have a fixed direction, which is 1, and you can have the x that you want, you only have these vectors, but you are missing one direction. So with these directions, you can construct all the lines in the plane, but you are missing one direction. What you cannot construct with this set is the horizontal direction, since you always have a vertical component. The way to construct the horizontal direction is this element. This element gives you the direction you are missing, which is the horizontal direction. So this is the way to think of homogeneous coordinates, and in the complex projective plane, this is a P, you need not 2 but 3 elements. So you need x, for instance, x, y, and z, or z0, z1, and z2. And you can also take this convention that you fix one coordinate to be a 1. But if you fix one coordinate to be a 1, then you have to you can write CP2 as these coordinates, as the set of these coordinates, 1, x, y, z. But then you also need for any x and for any y and z in R. But then you also need other directions that are missing here, since it's the same situations. You are missing some directions, some lines here, some one-dimensional subspaces, I would say. And you need also to consider points of this form for any x and z in R. So basically, homogeneous coordinates are coordinates in which, if you take another point, which is in which all the components are multiples but the same factor of the first point, it's the same point, thanks to this equivalence relation. I don't know if it solved your doubt, but I mean, CP2, it's a 4-dimensional manifold. We cannot draw it, but if we could, we can write RP2, which is like an Euclidean space with the points in the infinity also included, but instead of RP2, CP2.
That was an excellent explanation. I would have liked to have Pau Mir as a professor in when I was studying these things of the projective geometry. I mean, there is a whole world behind this explanation, which is projective geometry, that many of you know how it started. It started with paintings, okay, with the idea of perspective in the paintings, and this infinity was the point of the perspective. So we have a raised hand here. Do you want to ask a question?
Hi.
Hi.
Hi, Professor. I have a question.
Okay.
You used the Hamiltonian function in exercise 4. Could you talk more about the applications of Hamiltonian function? 就是 I want to know the applications of Hamiltonian function in other fields.
Wow. Applications to Hamiltonian functions of other fields. This is a very good question. Yeah. It's not, I mean, it's a question for I think it's a question for another session, because of course, I mean, can we apply the theory of Hamiltonian functions to other fields? We have seen now, thanks to Pau, the connection to algebraic geometry. That's what we have seen. Indeed, toric manifolds are a good invitation to applications in algebraic geometry. But there are applications, for instance, in fluid dynamics. And what I will do is to use, I mean, we have introduced already, I mean, we have seen applications to celestial mechanics and to astrodynamics. That was a little bit our initial motivation example, but there are also applications to fluid dynamics. And I will explain one application to fluid dynamics of this thing. This connects, indeed, this will be a connection point with the course of Boris Hessing that some of you are following, because this will be the point in which the two courses collide. And this is just to mention some of the applications, okay?
Okay.
Well, let's say, we could say that anything that has to do, this is a very good question. Thank you for the question. It's a deep question. And what I will do is, like, we will see, I hope that next class can be clarifying to these applications in celestial mechanics, because we will say, you know, finally, look, we are going to find an application of this to celestial mechanics. And the application is, you send this a satellite and it comes back. You say, oh, this is an application, right? And
okay.
Yeah, other applications are to fluid dynamics. The application to fluid dynamics requires that I explain the contact geometry, which is what I will do on Thursday. Maybe the application to fluid dynamics, there are like a very easy application that we will see on the last session, and another application that you will see in the public talk. I'm giving a public talk about fluid dynamics and these guys on the 11th of October. This is something you know, it's advertised. And well, in that talk, I will, because it's a public talk, I will skip details. It's going to be hand waving, but this is a whole world of applications. So yeah, does this answer your question? I'm answering your question saying this is a good question, and I'll try to give more examples in the next sessions.
Yes, thank you, Professor.
Thanks to you. Thanks a lot for the participation of all of you guys. You made this class much more richer than we had thought. I mean, we have touched, I think, everything, okay? And we had this categorical touch of Pablo. We had this algebraic geometry appearing now at the end, and this fantastic explanation of Pau Mir. You are the perfect professor in projective geometry. And we will move on to this obstruction theory on Thursday. With the introduction that, I mean, commenting some of problems that are already solved, but I think it's good. It's a good introduction to the session. And then I'll move to this contact, to the singular contact, and how this is useful somehow to find if the satellite will go back to you. Think, when the satellite goes back to you, this is a periodic orbit. So we will discuss the problem of periodic orbits on Thursday. Okay, I'll see you there. And thank you for being there still at the end of the course.
Hi, Professor. I have a question.
Yeah.
I see many times simple manifold. So I want to know what's the relationship between B symplectic manifold and simple manifold.
B symplectic and symplectic. That's what you're asking. Yeah, indeed, we saw this. And this was, I mean, the example that Pau did at the end, it was a very good example. He was saying, look, I can look at this manifold as symplectic, bisymplectic, how are they connected? I mean, I explained too briefly, and maybe it's good that I go back to this on Thursday, that there is a relation. And the relation is that sometimes when we have a bisymplectic manifold, okay, we can, in a way, desingularize. Connecting to the image of Pau is that essentially we can paint in gray this red line that corresponds to the criticals. And you cannot always do this. There are obstructions, topological obstructions to be able to do it. But the conclusion is that if your manifold, the singularity that you may have, as we saw in the restricted three-body problem, doesn't have to be one, it can be three. In the restricted three-body problem, remember we had 1 over x3. So the message is, when the exponent is even, okay, you can desingularize to a symplectic manifold. When the exponent is odd, you cannot. The best you can do is to obtain what is called a folded symplectic manifold. Maybe it's good that these are the singularization theorem that I mentioned, but this was 2 sessions ago, maybe too quick, okay? Maybe the plan for the next session is Joachim starts with obstruction theory, which is connects very well with this question. Then I recall the desingularization. And then the funny thing is that this singularization works better for one-fourths. So then I will introduce the contact and so on. I don't know. This answers your question. I mean, you're asking very good questions, but too general to reply in 1 minute.
Okay,
Like I have to
thank
write
you.
down. Okay, that is a good question. Okay, guys, thanks for being here. I think for you in China, it's a bit late. It's time to go to sleep. And Chinese people go to sleep or watch a movie, or I don't know, or read a book. And my collaborators and super professors, Joaquim Brugués and Pau Mir, the heroes of the day, have to go to eat. Okay, it's late for them. Joaquim, for him, is extremely late. It's almost tea time. Okay, and Pablo, thank you for your collaboration. So I propose that we finish here. Thank you, Anastasia, for clapping and for being here. And I'll see you very soon. I'll see you on Thursday. Okay, come back. See you soon.
See you
guys.
on Thursday. See you.
Thank
See you, guys.
See you.
Thank you, Chung. Chung, say hi to Amadeo when you go for lunch. Okay,
Oh,
bye.
yes, yes, of course. All right.
Bye.
Yeah, he mentioned
Have
he
fun.
didn't see you for 1 year. He said that